Analysis on the impact of feature reduction on time series data. Time series classification is the act of assigning discrete categories or classes to time series instances. This has many practical applications in a wide variety of areas, such as in ECG data, weather measurements, the Industry 4.0 revolution, fraud detection, and so on. However, the extremely large volume and high dimensionality of time series data can make it difficult to perform such analyses. Hence, this project aims to explore the most recent advances in automated feature engineering for time series classification, focusing on two techniques, Catch-22 and tsfresh. This is important because automated feature engineering techniques are better at selecting the optimal feature set, which can significantly reduce computation time while maintaining an acceptable level of accuracy. Automated feature engineering techniques also reduce the need for subject matter experts in specific domains, which can be costly and difficult to hire. Lastly, unlike black box methods like neural networks, features generated from the automated feature engineering techniques usually have a physical interpretation which allows scientists to understand the underlying dynamics and mechanisms of the system. The two selected pipelines are Catch-22, which stands for the canonical time series characteristics selected through highly comparative time series analysis, and tsfresh, time series feature reduction using scalable hypothesis tests. Now we will describe the methodology of the Catch-22 technique. This is an overview of the entire algorithm, and we will go in depth into each step. For the first step, Catch-22 uses the HCTSA toolbox to generate more than 7,000 features from the raw time series data. The HCTSA toolbox is made by the same group of researchers. For the second step, Catch-22 performs an initial filtering to remove any features that are not applicable to the specific time series. This could be because the time series does not have enough values, or it could be too short for this feature to calculate. For the third step, Catch-22 performs a statistical prefiltering step that removes features that do not perform better than random chance. In this step, Catch-22 performs 1,000 classifications on the datasets after randomly shuffling the class labels in order to generate a null accuracy distribution. Then, Catch-22 performs classification using the correct class labels to get a true accuracy, and calculate the p-value of the true accuracy being worse than random chance. Lastly, Catch-22 combines the p-values across datasets and removes those below the chosen significance level. For the fourth step, Catch-22 does performance filtering to choose the features that have the best classification performance. Catch-22 calculates the accuracy for each feature on each dataset and combines them to get a single combined accuracy score. Then, the features are ranked according to the combined accuracy, and only the top features are selected. In the last step, Catch-22 performs redundancy minimization by clustering the features according to their Pearson correlation distance using complete linkage hierarchical clustering. Then, the best features in each cluster are chosen as the final feature set. Now we will analyze how tsfresh works. For the first step, tsfresh generates around 700 features from the time series data using 63 time series characterization methods that they have implemented themselves. In the second step, in order to select the best features, tsfresh performs one of three types of hypothesis tests for each feature, depending on whether the feature value and class labels are binary variables. After this step, we obtain the p-values for each feature on a particular dataset. In the last step, tsfresh corrects the p-values for multiple testing using the Benjamini-Uccelli procedure and rejects those features with p-values above the threshold to obtain the final feature set. The two pipelines were implemented on a local Windows 10 computer and were compared using the following metrics: class balance accuracy, F-score, 5x2 cross-validation test, and computation time. In terms of class balance accuracy, the two pipelines perform approximately even, with tsfresh performing better on 45 out of 75 datasets corresponding to the circles below the dotted line, and Catch-22 performing better on 30 datasets corresponding to the crosses above the dotted line. However, on those datasets where tsfresh performs better, tsfresh seems to perform significantly better than Catch-22, exhibiting an average of 6.65% better accuracy corresponding to the larger distance from the dotted line. Following which, we stratified the scatter plots by various properties of the time series dataset, such as by the dataset type. tsfresh seems to perform significantly better on simulated and ECG time series, while Catch-22 performs better on device time series. Stratifying the datasets by length, tsfresh seems to perform significantly better on extremely short datasets of length below 200 and lengths more than 1000. Lastly, stratifying the datasets by number of classes, tsfresh seems to perform better for 78% of the datasets with more than 6 classes. All in all, tsfresh and Catch-22 may have different niche areas, but given the small sample size, these results are far from definitive and more studies still need to be done. Moving on to the next metric, F-score, we see that Catch-22 seems to perform significantly better than tsfresh for approximately 3/4 of the datasets, with a higher average improvement in performance of 8.7%. Given the small number of datasets in which tsfresh performed better, there was no point further stratifying these scatter plots. It seems that Catch-22 may be the preferred method if a high F-score is required. For the next metric, we use the 5x2 cross-validation tests to determine if the differences in performance of the pipelines were statistically significant. If the p-value of the tests is less than the chosen significance level of 5%, the difference in performance is statistically significant. Based on the results, the difference in performance for a majority of the datasets were not considered statistically significant for both class balance accuracy and F-score. However, the 5x2 CV test still corroborates some findings, such as tsfresh performing better than Catch-22 on class balance accuracy in a few cases, and there being more datasets where there was a significant difference in performance for F-score than Catch-22. Lastly, in terms of computation time, Catch-22 seems to take a much longer time to complete. Here we see Catch-22 takes an approximately 37,000 minutes on average, while tsfresh takes approximately 27,000 minutes on average to run. These results are a vast underestimate, as certain portions of the Catch-22 pipeline could not be easily measured. If the full pipeline of Catch-22 were to be considered, the actual computation time of Catch-22 is likely to be an order of magnitude louder than tsfresh. In conclusion, Catch-22 seems to perform better in terms of F-score, while tsfresh seems to perform better for class balance accuracy. Also, Catch-22 requires significantly more computation time, but could still be acceptable given that the feature engineering process is usually only done once, and especially if F-score is the desired metric for the use case. However, from the results of the 5x2 CV test, the differences in performance may not be statistically significant for some cases, and further analysis needs to be done on a wider variety of datasets to come to a conclusion.